Okay, so here they say that there's a meter stick that's held vertically above your hand. And I don't know, here's your hand. And not the best drawing, but whatever. And then the meter stick is held above your hand. And you're supposed to, what happens? When you see the meters, somebody else will release the meter stick and it starts falling down, and then you try to grab it with your fingers. And let's see. Let's say after they release it, you see it start falling, and then you react, and then you were able to stop the meter stick from falling. But of course, it falls down a little bit before you finally react. And in part A, what you're supposed to do is figure out the relationship for your reaction time in terms of the measured distance. So what I think is that, like, okay, so you could see for the meter stick, you could measure how far the meter stick went past your fingers before you were able to stop it from moving. And when we're thinking about the relationship there, a good equation to use would be something like delta x, which is the distance traveled by an object, is equal to the initial velocity times the time that it travels, plus 1/2 the acceleration of the object times the time that it travels squared. Now, what's good is that at the very beginning of this thing here, when the object is still released, technically the velocity of that object at the very beginning is 0. So initial velocity is 0. The accelerate so this VIT here is really 0 times time, which is going to be just 0. So we can kind of like get rid of that term in our equation. It doesn't matter. And then now we basically have 1/2 AT squared here. Another thing that we know in here is that the acceleration of this object is the acceleration of the object due to Earth's gravity. So the acceleration here would be the number called g, where g stands for the acceleration due to Earth's gravity, and that's measured at 9.8 meters per second squared. So this delta x in here in the original equation is actually the distance that you measure on the meter stick. So I'm just going to call that just d to be consistent with what we're trying to work out with here. So d is equal to 1/2, and then, I'll just say that's g. And what we're supposed to solve for is the relationship for your reaction time, so t, compared to the measured distance on the measure stick. Okay, so if we solve this equation for t, first we'd multiply both sides by 2. You'd get 2 times d is equal to gt squared. Then if you divide both sides by g, you'd get 2 times d divided by g is equal to t squared. And if you take the square root of both sides, you could write it as t is equal to the square root of 2 times d divided by g. So that's the relationship between time that it took for you to recognize that the meter stick was falling, and the, I should write this a little better, and the distance, which is the distance that you'll measure in the meter stick. Obviously, the longer the distance is, the bigger your time necessary to react. So the slower you are, basically. If you take a longer time to react, if you have a bigger t, then that means that you were slower to react. And if t were a smaller number, that would mean that you were faster to react. And if you were faster to react, then this d should be smaller. Okay, so in part B, it says, if the measured distance is 17.6 centimeters, which, by the way, if I convert it into meters by dividing by 100, would be 0.176 meters. I want to do that because the g here, I know it as 9.8 meters per second squared. Notice that uses meters. And so I want this thing to not be in centimeters. I want it to be in meters. Anyway, so if if this D here is 0.176 meters, they're saying what is the reaction time? Well, that's basically done in this equation here, where T, the reaction time, is going to be equal to the square root of 2 times the D value, which is 0.176, 2 times 0.176, divided by our G value, which is 9.8 meters per second squared. If we toss that into our calculator, let's see, we'll get, just put it over here, the square root of 2 times 0.176 divided by 9.8, and that'll give me 0.1895. I guess I could round that to 0.19. So that'll be 0.19. The units will be seconds. So in part B, if it took you, if the D was 17.6 centimeters, otherwise known as 0.176 meters, then that would mean that your reaction time was that it took you 0.19 seconds to react to the meter stick being released. So that's the end of that problem.